Ladies and gentlemen, it's time to talk about the chain rule. Here's the statement of the chain rule. If h of x is a composition of two functions, f and g, meaning that when you plug g of x into the input spot for f and take the composition of both functions, then its derivative is given by the product of the derivative of the outer function f evaluated at the inner function g times the derivative of the inner function g. Now this looks really complicated, and I'm sure you're thinking there's no way I'm going to remember this, but this formula that I've written down is somehow harder to understand than just computing with the chain rule in practice. So let's look at the formulas for a bit, try to get the hang of it, but what I really want you to get out of this lecturette is how to compute with the chain rule. So before we get to that, here are some other ways of writing the chain rule. First of all, I can use the circle notation for composition. This is the same thing as h, it just means compose f and g. So I'm saying the derivative of that composition is again f prime of g of x times g prime of x. I can rewrite that again in a slightly different way like this. The right hand side's the same, and I've just changed the derivative of the composite to the d by dx notation for taking the derivative. So we just have the derivative operator being applied to the composition f of g of x. And I can write it in yet another way, like so. And this looks like a complete mess. What's going on here? The left-hand side's the same. We're taking the derivative of the composite. What's going on here? I've used a new variable u. Okay, so I'm setting the output of g of x equal to u, and instead of writing f prime of g of x, I've taken the derivative of the outer function f with respect to u, and then I'm evaluating at that inner function g. So derivative of the outside evaluated at the inside. And again, we're multiplying by the derivative of g, but now using the d by dx notation. You should never write this. I'm sort of purposefully writing this down just to show you how complicated different notations can be, but I think it's important to be able to use the different notations in calculus. In particular, although this looks like a mess, it actually gives us one of the most elegant ways of writing the chain rule that there is. Here we go. So we're going to make some abbreviations. U, this auxiliary variable, it's just a name for the outputs of g, and y, that's the name for the outputs of f. That's how we usually think of the y-axis. That's the outputs of the function, right? So if we write u and y for the outputs of f and g, then we can abbreviate. This whole f of g of x, that's an output of f, so I'm just going to call it u, and then I put that, if we write u for the outputs of g and y for the outputs of f, then we can write this formula in a very elegant way. So I'm going to sub in y for the outputs of f here. And now instead of writing y in the parentheses, I'm just going to put it upstairs. That's the old classic notation, dy by dx. That's what we have right here. That means the derivative of f of g of x with respect to x using this abbreviated notation. The second term, super complicated, it just means the derivative of y with respect to u. So that's our shorthand for it. The final piece, the derivative of g with respect to x, since the outputs of g are called u, we would write that as du by dx. So now the chain rule is just a simple little formula. It looks like one fraction being equal to the product of two other fractions, and you can kind of think about the du's as being cancelled. That's a good way to remember it. It's not literally true. These aren't literally fractions. It's just notation for the derivative, but it's good intuition for what's going on here. Let's practice computing derivatives using the chain rule. The first step is always to identify the inside function and the outside function. In other words, to find the function you're trying to take the derivative of as a composition of functions. What do I mean? This piece here, x cubed minus 2 over x, that's the inside function. Why is that? Well, it's a function. It's a function of x, and it's being plugged into the square root function, right? We can think of this as a multi-step process where first x is taken to x cubed minus 2 over x, and then we take the square root. The outside function is the last thing that happens in terms of the order of operations. So in other words, the outside function, if we're going to use the f notation, it's just the square root function. It's the square root of something, in this case the square root of x cubed minus 2 over x. So that inside function, we'll use g for the inside function, that'll be just x cubed minus 2 over x. So we've separated what we're going to take the derivative of into an inside function and an outside function. So just to make things abundantly clear, notice that the overall function, without the derivative, I'm just thinking about the function itself here just to illustrate what I mean. This is precisely the composition of f with g. Check it out. If I plug g into f, then I'll get this original function, right? If I take this formula for g, the x cubed minus 2 over x, and I plug that into the f function, I'm taking its square root, I get exactly the square root of x cubed minus 2 over x. So this is a composition of functions. That's the sort of thing that we use the chain rule to take the derivative of. Okay. So now let's actually take the chain rule. Before we do that, we first have to compute the derivatives of f and g individually. Let's start with the inside function. So let's take the derivative of g. Well, the function g is x cubed minus 2 over x. We're going to be using the power rule, but let's remember how this goes for the 2 over x part. The x cubed I'll leave the same, but I'm going to write 2 over x as 2 times x to the minus 1. That's because dividing by x is the same thing as multiplying by x to the minus 1. So now we can just use the power rule on each piece. We bring down the 3, subtract 1 from the exponent. Similarly, for the next piece, we bring down the minus 1, and then we subtract 1 from the exponent. There you go. So that's the derivative using the power rule for each term in the sum. And let's simplify a little bit. We'll have 3x squared. We have a minus 2 times minus 1. 2 wrongs make a right. That's just a positive 2 times x to the minus 2. Groovy. Okay, what about the outside function? We also need to take its derivative, but here's the crucial thing. We're taking the derivative of f with respect to the inner function, so to speak, as a single piece. So we're going to be taking the derivative of f with respect to u. In other words, we're just taking the derivative of the square root of u. Well, how do we do that? Again, let's just rewrite that function before we take the derivative. That's u to the 1/2. I'm writing the square root function as u to the power 1/2, because then I can find the derivative using the power rule. The exponent comes down, and then I subtract 1 from the exponent. Awesome. Now in this case, I am going to rewrite that in terms of the square root function. Again, in terms of square root notation, this is the same thing as 1 divided by 2 times the square root of u. Let's write it that way. Okay, great. We're all ready to apply the chain rule. Here we go. So remember, we're computing the derivative of this composite function. That's the square root of x cubed minus 2 over x. And now that is equal to the derivative of the outside function. That'll be f prime evaluated at the inside function, no derivative. That's what the chain rule says. You just plug in g of x into the derivative of f, and then we multiply by the derivative of the inside function. That's just the statement of the chain rule. Okay? So, what does that say in this case? Well, we figured out the derivative of f with respect to u. It's 1 over 2 square root of u. So I need to plug in g of x for u in this 1 over 2 root u function, the derivative of f. Here we go. I have 1 over 2 times the square root, but now it's not of u, it's of g of x. And I'm going to leave some room because g of x has multiple pieces. What was g of x? It was x cubed minus 2 over x. Alright, so I've plugged in the function g of x into the derivative of f. And now I'm going to multiply by the derivative of g. We just computed that up there. It's 3x squared plus 2 times x to the minus 2. Okay, so we've applied the chain rule. It's the derivative of the outside evaluated at the inside times the derivative of the inside. That's the answer. Honestly, we could leave it like that if we wanted to. Let's at least write this using a single color and as a single fraction. This piece is all being multiplied by the fraction, so we can move it upstairs like so. And now I am going to write the x to the minus 2 as 2 over x squared. So that's this piece up on top. And then downstairs I have 2 times the square root of x cubed minus 2 over x. Like so. That's the derivative. In order to apply the chain rule, we need to figure out which part of this function is the inside function and which part of the function is the outside function. Now, 1 over x, that's the first thing that happens to x. That part's going to be the inside function. After we take 1 over x, we apply tangent. So tangent is going to be the outside function. You'll start to get the hang of recognizing these compositions. There's an inside part and there's an outside part. Okay? Now this time I'm not going to write this as a composition f of g of x, using those letters, right? It will be a composition. It's the composition of 1 over x and tangent. But I think it's useful to see the chain rule in action using lots of different notations, different mechanisms. You should find what works for you. Okay? Speaking of u, let's take the derivative of tangent with respect to u before we go any further. That's because we know in the chain rule we have to take the derivative of that outside function at some point, so let's have it handy. We computed the derivative of tangent, which is sine over cosine, using the quotient rule earlier, and we got secant squared. Derivative of tangent is secant squared, so we're going to use that fact here. Okay, and now I'm not going to do any other preparations this time. I'm just going to go ahead and go straight to applying the chain rule to show you how you can do the calculations in different ways. You'll get the same answer every time, of course. It's mathematics. It's the name of the game. But I think it's useful to see this procedure done in different ways, then you can find what works for you. So we're taking the derivative of tangent of 1 over x. I've shown you how it's a composition using the colors here. And the chain rule says that's equal to the derivative of the outside. The derivative of the outside function in blue, that's secant squared. So here's the derivative of the outside. It's the secant squared function. And now, where are we evaluating the derivative of the outside? We're evaluating it at the inside function without taking the derivative. So I just plug in 1 over x, the inside function, into the derivative of the outside function. And then I multiply by the derivative of the inside function. So let's use the d by dx notation for that, because we can take that derivative in the next step. So that right there, that's the chain rule. I've written it not in terms of f and g this time, but it's the same thing. Check it out. Here I've evaluated the derivative of the outside function, that was secant squared. I've evaluated it at the inside function. I've plugged the inside function, 1 over x, into the derivative of the outside function, but without taking the derivative of the inside function. You might think that you need to take the derivative of this piece there, but you shouldn't. You should leave that alone and only touch the outside function with the derivative operator. The derivative of the inside function comes into play in the next step when we multiply by the derivative of the inside function. So here, this piece, what is that? That is the derivative of the inside function. We multiply afterwards by the derivative of the inside function. That's the multiplicative nature of the chain rule. We're amplifying rates of change by multiplying them together. The two-step process, the rates of change of each individual part multiplied together, they amplify each other. Okay, cool. So far so good. Now let's evaluate. I'm going to go back to just using black ink for the parts that we've already done the work for. Okay, so secant squared 1 over x. That's not going to change at this point. I'm just going to leave it alone. But we still need to take the derivative of 1 over x, right? This part right here. What's the derivative of 1 over x? Well, thinking of 1 over x as x to the minus 1, here I'll write that step. It's always good to remember how that works. I rewrite 1 over x as x to the minus 1. And then I can use the power rule to evaluate that derivative. What do I get? I bring down the minus 1, and then I subtract 1 from the exponent. At the end of the day, when the dust settles, what do we get? This minus sign is being multiplied by everything. Notice that this is a bunch of terms being multiplied, so I can bring that minus sign out front, and I get secant squared of 1 over x times x to the minus 2. And I can write that as 1 over x squared. Let's do so. So that is the derivative of tangent of 1 over x using the chain rule.
I play my part on life's stage. I tell what I can to form the perfect answer. But that answer cannot come before all are ready to hear. So I tell what I can to form the